We present our work on meta-learning curiosity algorithms, and this is work done at MIT CSIM. Consider an RL agent interacting with an environment via actions, and then receiving states and rewards. This RL agent is running a particular algorithm, which is fixed, in this case, for example, PPO. These algorithms work well when the setting has dense rewards, but when the setting has sparse rewards, it's not very hard to do exploration and gain any kind of knowledge from this. In these cases, we would like the agent to explore efficiently. And so what we do is we propose to add a curiosity module. This has also been proposed before, that will receive rewards, states, and also the actions, so all the information, and will give the agent a proxy reward or hat that the agent can maximize. Now this RL algorithm will greedily maximize the proxy reward or hat, but it may be that by doing this greedy maximization, it's actually exploring in the overall environment, and so it may be doing an efficient exploration. Now the question is, what do we put in this curiosity module? There may be many options. One of them would be to just hard code. A human engineer can hard code the code for the curiosity module. Another one would be to put a neural network. And what we propose is to instead meta-learn it at the level of code. Let's see all the options and what they involve. First, we can see that the environment, the curiosity, and the policy form a dynamical system. In particular, each one has a form of memory or a form of state. In particular, the environment has a state which will get updated when the agent takes actions. The curiosity module also has to have some form of memory to keep track of what is novel and what is not. And then the policy is learning and updating itself. By gaining experience, it keeps updating itself via learning and doing updates in, for example, the neural networks inside the policy. Now, we can see that the environment affects the curiosity module and the policy by giving them states and extrinsic rewards, which we denote as E in this case. Then the curiosity module gives rewards to the policy, and then the policy in turn affects the state of the environment and the curiosity module by giving them actions. This not only runs for a few time steps, it actually runs maybe for a whole lifetime of the agent. And notice that if we want a curiosity to be useful, if we want exploration to be useful, usually exploration needs to last for a long time for it to pay off. So in general, it's going to be thousands of time steps, hundreds of thousands of time steps, even a million time steps. Now, what do we want? We want the overall curiosity to encourage the agent to explore, so that this exploration exposes it to novel experiences, which in turn will lead to more learning. And this efficient learning eventually will lead to high rewards over its whole lifetime. If we look at it, though, these lifetimes can be at the very end of the lifetime of the agent. So these rewards can be at the end of the lifetime of the agent, yet they may be influenced by curiosity at the beginning of the lifetime. And so how do we know which exploration was useful at the beginning by the rewards we got at the end? It's pretty much impossible to backpropagate through these million time steps to know how this affected. And also there's a credit assignment problem, because there's many different curiosity rewards that we gave the agent and many different actions that we took, and it's not clear how one influenced the other. So this is a very tough problem. Some people put this curiosity module as an RNN, but if you do that, because of the problems we mentioned in the slide before, you can only explore for very few time steps to be able to backpropagate through the RNN and also be able to do efficient credit assignment. So that's why it's a very short exploration, which doesn't match quite well the environments in which curiosity is the most useful. Second, because the RNN has weights and a kind of, in general, these weights do not generalize very broadly, this exploration, this meta-learning at the level of curiosity has only been able to generalize rather narrowly. So in this case, it only was able to generalize between different mazes, and different tasks consisted of going to different places in this maze. Another approach that has been taken is more similar to the one we're taking, which is these evolved policy gradients assume this curiosity module is still a neural network, and they're going to evolve the weights with an evolutionary algorithm instead of doing gradient descent. This eases the optimization and allows slightly better generalization properties, but these generalization properties are still quite limited. So in particular, they are able to generalize between training going to different positions to the right, and then they are able to test on going locations to the left. But this is still somewhat the same task, but different versions of the same task, and we would like to aim to something, a broader distribution. So to summarize, current meta-learning approaches based on transferring neural network weights usually generalize still rather narrowly. So for example, going at different speeds or going to different locations. In contrast, we would like to tackle different tasks. And to do so, we pick many different OpenAI gene environments, and we would like something that works well across these environments and transfer knowledge across these environments. How do we do this? In particular, it's a challenge because there are different types of inputs, different types of actions, and different types and different scales of time steps of exploration. We start with an environment that has image inputs, discrete actions, and a few thousand time steps of exploration. But then we also want to generalize to vector inputs, still discrete actions, and an order of magnitude more time steps. And finally, we want to test also on inputs that are vectors, continuous action spaces, and hundreds of thousands of time steps of exploration. We've seen how meta-learning approaches based on neural network weights and transferring neural network weights do not generalize this broadly. But human algorithms designed by ML researchers generally are able to generalize between very different experiments. So for example, if we think about GANs or transformers, the same idea is able to apply to different experiments by changing a few bits of the code. So for example, GANs are able to generate faces, but if you give them a different data set and change slightly the architecture, they can also generate map data or building data. And same for transformers, they can deal with sound and text at the same time with the same idea. What does this mean for curiosity? Well, in the case of curiosity, many humans have proposed algorithms before. So for example, Bourdais et al. Proposed random network distillation, and Pathak et al. Have proposed a couple of algorithms to do this efficient exploration and encode curiosity with a few neural networks. Notice that all of them have a kind of lines of code or mathematical formulas, and thus maybe we can also use a computer to generate a similar type of code or formulas, but now in an automatic manner. And now Martin will explain how we do this in practice.
So given that we want to search over some set of curiosity algorithms, we need a way to define the space of programs. And the way to define that space is by defining the smallest operations that can be composed to create some algorithm. So we've set up a so-called domain-specific language consisting of a few types of operations. First, we have different types of program inputs, either your current state, your next state, or the action taken between these two states. Second, we have neural network buffers. The weights of the neural network that will be persisted over time and trained on each time step. Third, we have a variety of types of operations. Some of these involve neural networks, such as the one here, which just runs a neural network, or the one here, which runs a neural network and then detaches the gradients coming into its output. But there's also other versions, such as vector operations, arithmetic operations, various loss functions, and some even more complicated ones that we'll talk about in a second. Fourth, we then specify one of these operations as providing the output of the program. This output is the reward that will be given to the agent in its environment. So in random network distillation, this output is defined as the L2 distance coming out of these two neural networks. And finally, we're able to define some loss function. So in this program, we also use this L2 distance as the loss function itself. And these gradients will backpropagate up to this neural network here but will be stopped from propagating all the way back up to this neural network here. So together, these different types of operations define our space of programs that we can search through. One of the ways that the space differs from spaces explored in other papers, such as in the neural architecture search community, is that we include some more complicated, potentially programmatic-like operations. For example, this program on the left has an ability to take an input and maintain a buffer of it over time, computing some operation on that internal buffer. This program here internally creates a nearest neighbor, which acts as a regressor, internally still maintaining some stream of its inputs. It's important to point out that the neural networks that are used in these programs are generally used as memory modules, rather, for example, than as components of the policy itself. Thinking about random network distillation again, this pink neural network up here is learning to memorize the output of this randomly initialized neural network number 1. The accuracy of this memorization prediction then will roughly correspond to how well or how many times the agent has seen a given state. So you can think of these networks as frequently doing something like memorizing the states that we've seen, although of course their precise purpose depends on the larger program and the overall configuration. One advantage of specifying our curiosity setup in terms of algorithms as opposed to neural network weights is that we can easily take a program that is effective in one domain and also try it in a domain that is totally separate. For example, it could have even a different input type in that we could take a program that is successful in a small grid world here and apply it to the acrobot domain, or it could even have a different action type, where we could take that program that was successful in grid world and apply it to, for example, Mojoko. We can do this by just taking the elements of the programs that either look at the input or look at the action and reconfigure them to the right shape of whatever input they're getting. So if we're getting an image, we could use a CNN. If we're getting a vector, we can use an MLP. And similarly, we can reconfigure different action losses. We're defining some reasonably large space of programs here, but of course there are many, many ways that you can think about setting up curiosity. We're only looking at a very small subset of this overall space. First off, we're just constraining ourselves to the domain where you use proxy rewards, where you're giving some proxy reward to the agent and encouraging it to learn from that. But you can imagine a variety of other different setups. For example, you could consider learning progress. You could try to learn some distribution over the domain, over the states that you've seen to recognize if you're somewhere new. You could do some more sort of complex state buffer manipulation of the sort that's not captured in our set of operations. Or you could, again, try something potentially totally different, maybe where you're generating potential subgoals for yourself and trying to find a way to exploit it there. Even within this proxy domain, though, there are still interesting questions about how you can, for example, take these intrinsic rewards that you're generating and combine them with the extrinsic rewards coming from your environment. Many existing papers have an approach of taking these two rewards and simply adding them together. We take a slightly different approach here and instead define a separate space of so-called reward combiner algorithms. These algorithms take both the intrinsic reward and the extrinsic reward, and also potentially a normalized time step, and combine these to create a final reward for the agent that takes both of these into account. This lets the agent then capture some sort of exploration-exploitation trade-off within this reward combiner program. And this program is also parameterized, of course, by the space is also parameterized by some set of operations, where here we use arithmetic operations, buffers, and some random sampling options. The best algorithm that emerges from this search process is one that has some nice intuitive properties. So it's listed on the left here, where we can see that the final reward is this formula combining the intrinsic and extrinsic rewards. And if we analyze this, we see that at the beginning of time, on the first time step, this is only the intrinsic reward. And on the last time step, assuming that the intrinsic reward is now small, this is only the extrinsic reward. So this program roughly interpolates between only intrinsic rewards at the beginning to roughly only extrinsic rewards. So it's roughly interpolating between only focusing on intrinsic reward exploration at the beginning to extrinsic reward exploitation at the end. And this was, again, the best program that was automatically discovered from the search process here. So we can then take this reward combiner algorithm and combine it with the best program that emerges from our curiosity program search. However, the curiosity program search is over an even larger space of programs, and this space is actually rather large. It consists of 52,000 programs overall, and if we tried to run each of these programs in some complicated domain, such as Mojoko Ant or Mojoko Hopper, then we estimate that this search process would have taken around 59 GPU years. This is much longer than we wanted to wait around, so we came up with a few optimizations that made the search process dramatically faster. Perhaps the most important optimization was simply not running every program in the most expensive environments. Instead, we take these 52,000 programs and evaluate them quickly in a proxy task that's much cheaper to evaluate. Specifically, we run them in this simple grid world navigation task and measure how many different squares in this world it's able to explore. We then take the best programs in this simple grid world and then test them in more complicated environments, testing the top 2,000 in the slightly more complicated acrobot and lunar lander environments, and only the top 16 in the even more expensive Mojoko environments. You could then imagine taking the best programs that emerged here and running them on a real robot, although we haven't quite done that part yet. So in practice, we only search algorithms within this grid world domain. And as we'll see in a second, we still see that the best programs in this domain perform very well, both in acrobot and lunar lander, the slightly more complicated ones, but also in Mojoko and Hopper, the much more complicated ones. So this was perhaps a surprise for us. The second way that we speed up this optimization process is by actually learning to predict a program's performance before we try it at all. So we take a program in terms of its raw structure, the raw operations that it contains, and convert it to a feature vector representing the present operations and the ways in which they're combined with each other. We then bootstrap a regressor that takes in this feature vector and predicts the program performance. We do this on the fly, where at the beginning of our training time, we have 0 training pairs, but after collecting the first few thousand data points, we begin to get some amount of prediction power. This prediction power is not incredibly strong, but we do see that it's enough to dramatically speed up the rate at which we find the best programs. Specifically, after only evaluating 50% of the programs, we had already found 88% of the best programs that we would have discovered if we had gone through and searched the full 100% of programs. This result was on a preliminary experiment only of 16,000 programs, but on our larger experiment, we still only evaluated 50% of the programs overall, which was immediately a 2-time speed up. So to summarize, the techniques that we use to speed up this combinatorial search, first, we just capped the number of operations per program to at most 7. This gave us those 52,000 programs overall. Second, we leveraged a program predictor to find the best programs without actually testing them. And this immediately cut our number of programs down to 26,000. Third, we used proxy tasks, specifically running in grid world, to allow ourselves to search efficiently. Fourth, we use a trick where we make sure that we don't run any programs that are functionally equivalent. This is slightly non-trivial because programs can be functionally equivalent even though they have dramatically different structures. So we use a technique where we feed these programs random inputs and then check if any 2 programs produce the same output on those random inputs. And finally, we measure the performance of programs as they're being evaluated live in a domain, and we'll quickly prune any agent that isn't achieving good external rewards. So for example, in grid world, if an agent is just sitting in the corner, repeatedly running into the wall, this trick will detect that and stop that agent's rollout. Put together, we were then able to leverage those efficient search techniques to search through our space of 52,000 programs reasonably efficiently. And we find some potentially surprising results. So first, the vast majority of programs in this space are simply very poor exploration algorithms. Here, every dot labels an individual program, each which was evaluated by running an agent from a brand new start throughout its full lifetime on grid world. We then sort the performance of each of these programs by, we then sort these programs by their mean performance horizontally, and also display that performance vertically. So we see that the vast majority of programs fall in this band in the middle, where they result in very noisy, where they find very noisy performances on different rollouts, and where our exploration program basically isn't providing them with any signal at all. However, we do find a tail of around 0.5% of statistically significant programs. These programs perform significantly better than this large chunk of random programs down here, and they also lead to good exploration in the domain. We then see that these top 0.5% of programs that do very well in grid world also transfer to doing well in more complicated domains. Here, we look at the performance in terms of its correlation to lunar lander and acrobot. In both of these plots, we're plotting performance in grid world on the bottom and performance in the other domains on the vertical domain. We can see that the programs that perform well in grid world all perform well in lunar lander as well. And similarly on acrobot, the programs that perform well in grid world also generally perform well in acrobot. So grid world here is able to act as an effective filter to find good candidates for curiosity algorithms. The top algorithms that we find are in fact statistically equivalent or sometimes better than the human design algorithms from the literature that we mentioned previously. We've drawn these algorithms in green crosses here on this plot that I had showed before. And we can see that in lunar lander, these human designed algorithms are roughly equivalent to our best performing algorithms. And in acrobot, our algorithms are slightly better. We also look at performance in the more computationally expensive and potentially more complicated domains of Mojoko, Ant, and Hopper. Here, we're plotting the error bars for each of our best programs in these domains. So we see that the baseline algorithms perform quite poorly in those domains, but the meta-learned algorithms that emerge from our search are statistically equivalent to the human-designed published algorithms from the literature here. So when we go through these top 16 algorithms, the ones that we're evaluating in Mojoko, we see that they're all variants of two main classes of programs. We think it's interesting to look at precisely what those programs are. So Fran is going to talk through them now.
As Martin was saying, the output of our search consists of a few algorithms, and these algorithms are interpretable because there are some pieces of code, essentially. Compare this to when we meta-learn a neural network weights, where our output is a bunch of maybe thousands of numbers that are much harder to get insights from. So in this case, we found that the top 16 programs consisted of different versions of essentially two programs, which also gives us confidence that about the reproducibility of this approach. The first one is what we called fast action space transition, or we shorthand as FAST, and it's a very simple program. Essentially, it consists of a single neural network that takes as input both the current state and the next state, and evaluates both of them and tries to predict the action from one of them. So in particular, you can see it receives a loss function to correctly predict the action from the future state st+1. Now, since the states are not equal, you're going to predict something different from ST than from ST plus 1. And the difference in these predictions is the reward you give to the agent. So in particular, these rewards go in state where you predict a different action. Notice that this is different than taking a different action. So for example, imagine a random policy that every time took a different, that every time took an action at random, it would very likely keep changing actions at every time step. If the reward was take a different action, this policy would receive a very high reward. But actually, it would not receive a high reward in fast action in our algorithm fast, because a predictor that tried to predict this random action would essentially output the uniform distribution for any state. And therefore, the prediction would be constant, and it would not change from ST to ST plus 1, therefore giving a random policy a very low score. And something that is also indicative is that if the state is very different from the previous state, it's very likely that the network makes a different prediction. Whereas if it moves to a very similar state, the network is likely to give a very similar prediction. Therefore, it's implicitly trying to reward moving to a different state from the one you're in, which is an intuitive thing to do. Moreover, if you're in a state where you haven't quite explored it yet, it's very likely that the predictions are somewhat random and they're therefore differ between each other. And this is also a case where you want to reward the agent. Therefore, even if it's a very simple algorithm, it's very effective. The other one was actually the opposite. And Martin and I actually didn't understand it at first. And it actually took going to NeurIPS and finding a student from Berkeley and talking the three of us for quite a bit before we actually understood it. In hindsight, it has some similitudes to cycle consistency, which is best known in the GAN literature. And the idea is that if you have a way of moving from a space to another space and then back again, you should end up in the same place you started. So for example, if you're trying to convert zebras to horses and horses to zebras, you can apply both mappings, and you know that if you convert a zebra to a horse and then a horse to a zebra, you should end up in the same image you started with. This program essentially leverages a similar intuition, but in this case, in the case of curiosity. And the idea is similar. If you have a forward model and a backward model, if you apply the forward and the backward, you shouldn't end up in the same place. Let's look concretely at how this looks like. This algorithm has 3 neural networks. The first one is the simplest one, which is a random but fixed neural network, similar to the one you have on random network distillation. Notice that since the arrow coming out of it is black, this means it does not get any gradients from it. The reason it does not get any gradients is that if you look at the losses, which essentially just make 2 losses for each prediction, so there is 2 predictions in the algorithm, shown in pink, but the random network only acts as a target. And when you're making a prediction, you don't backpropagate through the target, you only backpropagate to the network making the prediction and to the query that the network uses to make the prediction. So this is going to stay fixed. And then you have 2 other neural networks. This neural network number 3 acts as a backward model. We'll see later why. And this neural network number 2 acts both as this random embedding that should copy neural network 1, as in random network distillation, and also as a forward model. Why is this the case? Well, we can see that if we look at the objective of neural network number 3, what it essentially says is, I want you that if you apply the backward model plus the forward model on a random embedding of state S, it should give you, again, there is a random embedding of state S. And so it's applying the cycle consistency of going back and forth. Therefore, this network should act as a backward model for this cycle consistency to hold. Neural network 2 has one of these terms is the same as the neural network 3, but there is an extra term which is essentially says that the backward and then applied to the forward of state ST plus 1 should equal the forward of ST. And that's why it's acting as a forward model, because the term on the left is essentially saying go back and forth from ST plus 1. So essentially you get ST plus 1, and this should be equal to the forward model applied to ST. And finally, there's the intrinsic reward, which is not quite using cycle consistency. It's doing slightly something different, which basically it's, again, it does backward and forward of a random embedding of state T plus 1. And it compares it again against doing the cycle of backward and forward applied at a state ST. So you can see it does this backward and forward, both at st+1 and at st, which initially should not be the same. So similar to the fast algorithm, it's making a comparison between st and st+1. This has the effect that if you move to a different space, to a different state, you're going to make different predictions. And also, if you haven't explored this this part of the space yet, your forward and backward model will not have learned the correct function, and therefore the cycle consistency is likely to not hold because you have not learned the proper models. And therefore, it rewards you in two ways. It rewards you for moving to a very different state, and it rewards you for moving to a part of the space where this cycle consistency will not hold, which is a sign that the models still have a lot to learn in that part of the space. In conclusion, the main takeaways of our work is that this approach of thinking about curiosity is an evolved mechanism that maximizes the reward over an entire lifespan, and that this lifespan is very long, is a fruitful endeavor to consider. Also, that we can increase meta-learning generality with program-like structures. In particular, we showed that if you learn at the level of algorithms instead of neural network weights, you can generalize radically compared to previous meta-learning algorithms. And finally, that it is possible to automatically design interpretable state-of-the-art machine learning algorithms, and we display it in the case of curiosity. For more information, please visit alatetal.com or Martin's GitHub for the code. Thanks for your attention.